Module 2 OCR A-level chemistry. Let's go. I'm not going to go over Module 1 because it's all practical stuff. Module 2 is the first real content. And this is minimized for efficiency, so everything on this is on the spec. First of all, you're going to have to be able to define the word isotope, and it's a same element with a different number of neutrons, and therefore it has a different mass. So in this example, we're using carbon 12, which is written here like it would be on your periodic table. 12 is what we call the mass number, which is the combined number of protons and neutrons, or particles in the nucleus, and 6 is the atomic number, which is just the number of protons. Now this is carbon 14, and as you can see, it does have a different mass number, but it still has the same number of protons, which makes it the same element, but it's an isotope because the mass number is different. And that's because where there were 6 protons and 6 neutrons, there are now still 6 protons, but 8 neutrons. Next on the specification, it asks you to describe what happens when you're consulted with ions. Now, like I said earlier, you can't change the number of protons without changing the element. So when you have a positive ion, rather than adding in a proton, you're just taking away an electron. And likewise, if you were to take away 2 electrons, you'd have a 2+ ion. And then obviously, when you go into negative ions, you start adding electrons. So the spec specifically asks you for the definition of 2 terms, relative isotopic mass and relative molecular mass. And they're the same definition, essentially. They are the weighted mean mass compared to 1/12 of the mass of a carbon 12 atom. And the only words missing here is it would be weighted mean mass of either isotope or atom or molecule or whatever you're trying to calculate the molar mass of. And you can find this mass using something called a mass spec, where any sample you put in is vaporized, ionized, and then sent up a tube. Heavier atoms are slower going up the tube, and they deflect less, which helps separate the masses. And the more ions that reach a certain point in your mass spec, the stronger the signal is. And on the x-axis of your output is something called MZ ratio, which is the mass to charge ratio. But where you have 1 plus or minus ions, your MZ ratio is equal to your molar mass. Now, this is an example of what a mass spec would look like. As you can see, you've got your MZ ratio on the bottom and your percentage abundance on the y-axis. And your 2 peaks there at 35 and 37. So now you take your percentage abundance and you multiply it by your atomic mass, and you add them together and you divide it by 100, and that will give you your relative atomic mass. And so for that example, we can say that the relative atomic mass is 35.5. And I forgot units here, but its units are grams per mole. Now, the spec expects you to predict the ions of any elements that aren't transition metals, and as you can see here, it's not really difficult. And it expects you to be able to apply these to binary compounds, which have 2 elements. In which case you always put the metal first and the non-metal after with the suffix "ide". As you can see here, the example is sodium oxide. It does expect you to know the name, charge, and molecular formula of 5 polyatomic ions. And unfortunately, it's just one of those ones you've got to learn either through practice or through sitting down and just memorizing them. But your only cation is ammonium, and then after that you've got 4 anions, which are hydroxide, nitrate, carbonate, and sulfate, and the charges are on there for you. A good way that I use is by using the non-ionized bit. So NH3 is ammonia, you chuck a hydrogen on there and it's NH4+. H2O is water, take away an H and you get OH-, etc, etc. You can use that for all of them, H2SO4, stuff like that. Next, it asks for the definition of a mole, and a mole is any amount of substance that contains 6.02 times 10 to the 23 particles of whatever you're trying to find the amount of. And the mass of 1 mole of substance is really easy to remember. because it's just the molar mass but in grams. So for carbon, molar mass of carbon is 12. 1 mole of carbon weighs 12 grams. And that means you can work out the number of moles by doing the mass over the relative atomic mass. So, some more definitions. Molecular formula is the formula containing the exact number of elements in a compound, whereas empirical formula is the simplest whole number ratio. An example of this is the molecular formula of hydrogen peroxide is H2O2, whereas its empirical formula would just be HO. Now, as well as define it, you're expected to be able to calculate the relative molecular mass. And it's nice and easy, it's just the sum of the atomic masses. So for H2O, there are 2 hydrogens and 1 oxygen, so 2 plus 16 is 18. You're also supposed to be able to calculate the empirical formula of a molecule. So in this question, we're expected to calculate the empirical formula of calcium chloride. And the way we're going to do that is we're going to pull our masses from the question, and we're going to pull our relative atomic masses from our periodic table to calculate our number of moles. And then we're going to calculate the ratio, which is in this case 1 to 2, so we can say the empirical formula is calcium chloride 2. Now, in the question, if it asked us to work out the molecular formula, this isn't much more difficult to do. In the question, it might say the relative molecular mass is 222.2 grams per mole. And all you have to do is work out the empirical formula, which we've already done, calculate its relative molecular mass, and then compare the two. So in this question, it would be calcium 2, chloride 4. Because if you have to double the relative molecular mass of the empirical formula, then the molecular formula must be double the empirical formula. You might also be asked how to calculate the ratio of hydrated salts. So, as you can see here, hydrated salts just means how much water per mole of salt is there. So, in this example, there are 5 moles of water for every 1 mole of copper sulfate. And we work this out in a similar way to how we worked out empirical formula. You do your mass over your relative atomic mass, and that gives you your number of moles. And then you do the same calculation with water. Now, you'll often have to find the mass of water by yourself. In the question, they'll give you the mass of the hydrated salt and the dehydrated salt, and all you have to do is subtract them. So, we compare and contrast our number of moles, and we get the ratio of a fifth. So the ratio of our hydrated salt must be 1 to 5. So a pretty common follow-up question might be, such and such actual value is different. Why? And it's because you've made 2 assumptions. You've assumed that all water is lost in the dehydration, and you've assumed that no further decomposition takes place. Now, moving on from solids, we're now going to look at liquids and gases. So here are some units, and you're going to need to know these unit conversions off by heart. And your calculation for the number of moles becomes number of moles is equal to your concentration multiplied by your volume. And you'll need to know the term standard solutions, but it's nice and simple. It's a solution that you know the concentration of. And you'll need to know what room temperature pressure means. And just a quick note, these are not standard conditions, but room temperature pressure means 20 degrees Celsius and 101 kilopascals. And at room temperature pressure, 1 mole of gas occupies 24 decimeters cubed, and that's assuming 4 major assumptions. And you'll also need to know these if you do physics, and that is that the particles move randomly, all collisions are elastic, particles are of a negligible size, and there are no intermolecular or electrostatic forces. And these assumptions allow you to use the equation PV equals nRT. Now, this isn't given to you in the equation sheet, but it's one of those things that through practice you'll just come to know like that. Now, this one involves a lot of unit conversions. So pressure is in pascals, volumes is in meters cubed, temperature is in Kelvin, and then the other stuff stays as it is. But always, always, always make sure to check your units, and R is given to you in the formula booklet. Now, this isn't a word you need to know the definition of, but it's an important word nonetheless. And stoichiometry is just the ratio of molecules in a reaction. And like we did previously, you can use these to calculate the number of moles in a reaction. Like here, we've just used it to calculate the number of moles of oxygen. Next, we have to work out the percentage yield, and it's very simple. It's the actual yield over the expected yield times 100. And what that means is your mass that you obtain in a practical will be less than how much you calculate in an equation like the one we did earlier. Now, when calculating the mass or the number of moles of a product, it's important you take into account something called the limiting reagent. And we use the term limiting reagent when one reactant is in excess or some are in excess, but at least one of them isn't. And we use the term limiting reagent because it limits how much product can be formed. You may also be asked to calculate the atom economy of a certain equation, and it's the sum of the desired molar masses over the sum of all molar masses times by 100. And this is used for the product side of the reaction, and it helps determine how useful a reaction will be. Now, moving on completely from reactions, we have the topic of acids and alkalis. Now, acids are solutions that release H+ ions when dissolved in water. Strong acids do so completely, whereas weak acids only do so partially. And the opposite of an acid is a base, and bases neutralize acids to form salts. And when you dissolve a base in water, you end up with something called an alkali, which releases OH ions. And you can see an example here, copper oxide, which is your base, reacting with sulfuric acid, which is your acid, to form copper sulfate, which is your salt, and water, H2O, which comes from the H+ from the acid and the OH of the base. You can also form salts through reacting metal carbonates with acids. So here, zinc carbonate plus sulfuric acid gives you zinc sulfate, which is your salt, plus water, plus CO2, which comes from your carbonate. Now, with the reaction of an acid and an alkali, you can find the concentration of a solution using something called titration. You can also use titration to identify unknown chemicals and find the purity of a product. And then with the titration, you can combine the two equations we used earlier to put into a grid system so you can work out your number of moles or your volume or whatever you're trying to calculate. And if you're struggling to understand that, there are some great videos online if you search up titration calculations, and I'll be doing some personally later when I've finished all the modules. Next up, we have something called oxidation numbers, which is a simple way of saying the number of electrons involved in bonding. Now, it's always 0 for elements. Things like O2 have an oxidation number of 0. It's also important to note that it's not the same as ionization, and so the sign comes before the number. Now, the sum of oxidation numbers in a compound is equal to its total charge. And that means we can use the charge to work out other oxidation numbers. So here, for example, if you follow the process, you know that nitrogen has an oxidation number of 5. And it's important to note that when they ask you for the name of a compound, you should include the oxidation number if it contains a metal with more than one. And you do this by writing the oxidation number in Roman numerals in brackets next to the metal. Here you can see 2 examples for iron. That should be +2 and +3, by the way, rather than 2+ and 3+. You may also have seen the method of like ite and ate suffixes, and they won't mark you down in a test for this. It is technically correct, but it's outdated and it's complicated, so I wouldn't worry about it. So hopefully you'll remember from GCSE the acronym oil rig. Oxidation is loss, reduction is gain. When it comes to electrons, this is absolutely true, but the opposite is true for oxidation numbers. It's nice and easy to remember because reduction is a reduction in oxidation number and oxidizing is an increase in oxidation number. Now, in this example here, zinc is oxidized and hydrogen is reduced. And for this reason, we call it a redox, which is a portmanteau of reduction and oxidation. And this is important, and we'll come back to it later, but for the moment, we need to talk about electrons. So for A-level chemistry, you need to know how many electrons each shell can hold, and they're written on screen for you here. This is different to what you were taught in GCSE, but it's not difficult to remember. Now, the reason it's different to GCSE is because you didn't know about orbitals, and orbitals are regions around the nucleus that two electrons could occupy as long as they have opposite spins. There are a limited number of orbitals per shell. There's one S shell, but there's 3 P shells, and that's because it can occupy the X, the Y, or the Z axis. Now, S shells are spherical, S for sphere, and P's are normally 8 or infinity shaped. I say peanut because it helps me remember P for peanut. Now, you don't need to know about D and F other than that they exist, and there are 5 D subshells. If it helps you remember, you can calculate the number of electrons per shell by using the subshells or vice versa. Now, there is a specific order to filling these if you're asked in a question, and it's the lowest energy first, and sometimes that means you have to put 4s2 before 3d10, but that's just the way it is, and it's easy once you remember it. But just a quick parish notice, always put the smaller number first in the answer to a question, even if your 3Ds aren't fully filled, always put them before your 4s, unless 3D just doesn't exist. Now, another thing you'll need to remember is to fill singly before you fill pairs. So here you have 2d3, which has 1 arrow in each box, and when you go to 2d4, then you start pairing up, and if they have opposite spins, they need to go in opposite directions. So I'm just going to hammer this point in. This is the order you should fill them up to 3D, but then when you do one, for example, this is the electron arrangement of bromine, 3D comes before 4s. Now, other than krypton, bromine is the last one you need to know, and its electron arrangement is like this. But if you don't want to write that all out, which why would you? You can write it as the last noble gas, so in this case argon, plus whatever electrons you've added up to that point. And this is really helpful if you want to double check your answers in the middle of a test. This little periodic table and the way it's set out in its suborbitals can help you know if you're in the right place-ish. Next, we're moving on to bonding, but before that, you need to know what cations and anions are. So cations are positive, and they're normally metal, whereas anions are obviously negative and can be any non-metal or polyatomic anion we went over earlier. Now, again, you should remember dot and cross diagrams from GCSE, but in case you don't, the electron from the potassium has transferred to the fluorine and is represented by the cross. So now fluorine has a full outer shell with 7 dots and 1 cross, and potassium has a full outer shell, which you can either draw as 8 crosses or just none because it's lost one. And then obviously don't forget your square brackets and your signs. And these will form what is known as a giant ionic lattice. And what that means is in an ionic compound, so in this example, sodium chloride, sodium plus ions will have 6 chloride ions around it, which will have 6 sodium ions around it, etc., etc., and it will go on forever, hence giant. Now, these strong ionic bonds mean that any structure has a high melting and boiling points because of the strong electrostatic attraction between oppositely charged ions. And the more charge an ion has, the higher the melting point because the stronger these electrostatic forces are. And because there's a positive and a negative end of the molecule, they dissolve really well in polar solvents. We'll go over polarity in the next video. However, higher charges can mean lower solubility, as it's more difficult for a polar solvent like water to get in between the molecules. Now, in its solid state, it doesn't conduct electricity because the ions are fixed in the solid, and so there are no mobile charge carriers to conduct electricity. But the second it is dissolved or it becomes a molten, the lattice breaks down and ions now act as charge carriers through the structure. Which means now if you were to put a current through it, it would conduct electricity. Now, unlike in GCSE, covalent bonds here are described as orbital overlaps and are the result of strong electrostatic attraction between a shared pair of electrons. Now, unlike ionic bonding, attraction in covalent bonding is localized, so it only creates small molecules, and you can see this with any diatomic gas. Now, they'll normally do this to gain a full outer shell, but a notable exception is boron. Boron only needs 6 valence electrons, purely because it's an exception to the octet rule. Now, the number of bonds an element makes depends on the element itself. So sulfur is group 6, but it's the third period, so it can hold up to 18 electrons. So it can arrange itself where it has 2 bonds, where it has 4, or where it has 6. And that creates variety in the shape of a compound. Quickly, before we do shapes, we need to talk about dative bonds. So here with our ammonium ion, you can see the H plus isn't welcome because the nitrogen has a full set of electrons. But what it will do is it will use its lone pair to bond with the hydrogen. And so when the 2 electrons are from the same element, we call it a dative bond and we represent it with an arrow. And you can measure the strength of these bonds, or any bonds, with something called enthalpy. Now, on to shapes. Electrons around the central atom determine the shape of the molecule formed because they're negative charges. They want to repel each other as much as possible to minimize the amount of force they're exerting. And this minimum repulsion allows it to maintain its shape permanently. And so, as we saw earlier with sulfur, the different number of electrons create different shapes. So the first shape is tetrahedral, and methane is a great example of this. Because the bonding electrons are repelling each other equally, you end up with a bond angle of 109.5. But just be aware, not all tetrahedral shapes have a bond angle of 109.5 because of lone pairs. Now, lone pairs are any pair that aren't used in bonding. And because they're not used in bonding, they sit closer to the atom, and so they repel other electrons more strongly. And so they force the bonding electrons closer together by about 2.5 degrees per lone pair. So here's an example of ammonia. Ammonia has 1 lone pair, but it's tetrahedral, so the angle is 107 because it's 109.5 minus 2.5. Now, it's important to remember that bonded regions act like electron pairs, and as complicated as it sounds, it just means double bonds don't repel each other because they're double bonds. So in carbon dioxide, even though there's 4 electron pairs, there's only 2 bonded regions, so it's linear, so the angle is 180 degrees. So next we have trigonal planar, which you can see here is 120 degrees. And we have octahedral, which is 90 degrees. When 2 different atoms are bonded, because nuclear charges vary and sizes vary, the shared pair may be closer to one element than it is to the other. And the attraction of the bonded atom to the electron we call electronegativity. And electronegativity increases across the group because charge in the nucleus increases and the radius decreases. It also increases going up the groups, and so we can say that fluorine is our most electronegative element. Now, we can use the pooling values to work out what kind of bonding is going on according to the electronegativity. Nonpolar bonds occur between either the same elements or elements with similar electronegative values. But in polar bonds, which is anywhere between 0 and 1.8, the electron pair is shared unequally, which creates polarity. So, as you can see in this example here, the bonding pair is held closer to the chlorine, and so we denote it as more electronegative, so we do sigma minus, and then for the H we do sigma plus. So here you can see water, and water is more electronegative at the top and less electronegative at the bottom, or electropositive at the bottom. And what this does is, even though there's a line of symmetry straight down the centre of the oxygen, there is an overall dipole at the top and at the bottom, and so we'd call this molecule polar. Now, while the same is true in carbon dioxide, that oxygen is more electronegative than carbon, there is no permanent dipole because the molecule is symmetrical, and so the two dipoles cancel out. Now, dipoles help us determine what intermolecular forces are used and where. There are three you need to know for A-level chemistry. Their names and enthalpy ranges are on screen now. We'll go through them one by one. First, we have induced dipole interactions, which you'll see I have called London forces. Now, these are quite complex, so bear with. Now, electrons can occupy anywhere in their orbital, and so at some point will create a dipole, like seen here. And because opposites attract, this occurs in every molecule along that chain, and this weak electrostatic force holds the structure together. And this on screen now is the definition you'll need to remember for your test in case they ask you what is an induced dipole-dipole interaction. Now, the more electrons something has, the larger its induced dipole is, which means greater interactions and stronger attractive forces. And that's why if you work your way down a group, they'll tend to become more solid as you go down. So the noble gases go from gases into solids by the time you reach radon. So hopefully you remember from earlier we said hydrogen chloride has a permanent dipole. And because it's not reliant on the random movement of electrons, this builds chains like the last one did, but permanent. Now these are slightly stronger because even though the electrostatic force is the same, they also have London forces or induced dipoles as well as their permanent ones. And so molecules with permanent dipole interactions will have a higher melting point. Now, it's important to remember that intermolecular forces and covalent bonds aren't the same thing, and when you're melting a substance, you're not overcoming the covalent bonds between the atoms, you're overcoming the intermolecular forces. And it's also important to think about solubility when it comes to intermolecular forces. So non-polar bonds are very soluble in non-polar solvents. And so it can get in between the molecules and weaken these intermolecular forces. However, the same can't be said for polar solvents because they can't get in between the molecules and so they can't break up these intermolecular forces. And with polar molecules, the opposite is true. They attract polar solvents to get in between the molecules and disturb their intermolecular forces. Although it has to be said that the solubility depends on the strength of the dipole in both the solvent and the molecule. But its solubility in non-polar solvents depends on the molecule itself. For example, here with ethanol, you have a polar end, but you also have a non-polar end, which will dissolve well in non-polar solvents. And then last on the list in Module 2 is hydrogen bonding. Now, it's a special type of permanent dipole where it contains an electronegative atom with a hydrogen attached to it and a lone pair. Now, this is a diagram, and if you are asked to draw it in an exam, this is exactly how you should draw it. Label your hydrogen bond, make sure you draw in your lone pairs and your dipoles. And like I said, it's not just water, but water will definitely be the most common example. Especially, it might ask you to use water as a solvent but give you a different polar molecule. So alcohols or things like that. Ammonia would be, I'd say, quite a common one as well. And then last thing, we've got to discuss how this affects water. For example, water is one of the very few molecules where its solid form is less dense than its liquid form, and that's because freezing water keeps the hydrogen bonds in place and it creates a large open lattice. And this means that when it's really cold out, ice sits on the top layer of any rivers or lakes or fresh water, and that's really crucial for life because it means the fish underneath it don't get frozen and die. It also has a higher melting point than expected because of how strong hydrogen bonds are. It has a really high surface tension and it has a really high viscosity. So that's going to be it. Thank you for watching. I really hope you enjoyed and I really hope it was helpful in some way. Module 3 will be next week, so feel free to join me then and I'll see you around. Bye.